Following what we discussed in last week, now we are ready to analyze active mode locking quantitatively. There will be two different approaches. The first approach is relatively easy. We will use a Gaussian pulse model to reach the steady state solution about active mode lock lasers. The second approach is more complicated, but also more precise, which will be based on coupled wave equations. Okay, so let's take the easier first. So this slide shows the strategy to get steady state solution. Okay, there are 3 steps. Step 1, we assume a Gaussian pulse of unknown amplitude and width. So the pulse shape has been fixed. It's of Gaussian shape. But at this point, I cannot explain why it must be Gaussian. It will be discussed later. If the shape is Gaussian, we still have 2 unknowns to be determined. One is what is the peak amplitude of this Gaussian pulse. The other is what is the width of this Gaussian pulse. These 2 parameters have to be determined by the parameters of these laser systems. This laser system consists of at least 3 components: the cavity, the gain medium, and the intensity modulator inside the cavity, right? So these parameters will determine what will be the amplitude and the width of the steady state pulse. Okay? In the second step, we have to trace the change of pulse due to every element. We have 3 elements in this figure, right? The cavity, the gain, and the modulator. Each of them will change the pulse a little bit. For example, the input pulse passes through the cavity. What would be the output pulse due to the cavity effect? So you can imagine at least the cavity loss will reduce the peak of the input pulse, right? And what happens when the pulse passes through the gain medium? You can easily imagine the energy will be increased due to the amplification. And what happens when the pulse passes through the modulator? And you can also easily imagine the pulse width will be reduced by the contribution of the modulator. Okay? But all of this will be quantitatively analyzed later. Now we just know the behavior qualitatively. Okay? So we have to trace the change using mathematical models to trace these changes. Okay? And finally, in step 3, we force the output pulse be a replica of the input pulse after 1 round trip. So simply speaking, the input pulse will be exactly the same as the output pulse after 1 round trip. If this condition is reached, we can ensure steady state is reached, because no matter how many further round trips take place, the pulse will be the same if output pulse equals input pulse. Okay? So by using these 3 steps, we are expected to get the steady state solutions to the 2 unknowns, okay? The amplitude and the width of the Gaussian pulse. Any question? Please.
The output pulse is just output, not one repetition.
Yes, round trip, right? So after 1 round trip, what is round trip? after passing through the cavity once. Okay, so it will reproduce itself. If this condition is satisfied, you can imagine no matter how many round trips, the solution is still the same. Okay. Good. Any other question? Okay, so let's go through the mathematics. Okay. The assumption of the steady state pulse. We assume the complex temporal envelope of the steady state pulse. So there are two key words already. First one is complex temporal envelope. Do you still remember what is this? We introduced this term in lesson 1, right? Small a of t. It is not the electric field itself, but after multiplying with the carrier term e to the j omega 0 t and taking real part, you can get electric field. But the envelope itself is a complex function in general, okay? You can have magnitude, you can have non-zero phase, okay? The second key word is steady state. That means this analysis approach only gives us steady state solution. We have no idea about the dynamics, right? From the initial noise all the way to steady state. In between, we have no idea what happens. This simple approach only tells us what is the steady state solution, okay? So pay attention to these key words. Here we assume the temporal envelope function is a real Gaussian function. So you have seen we have made very strong assumption because in general, envelope function is complex function. But we have already assumed it's a real function. We already sacrificing the possibility of phase function in steady state, right? So it has to be justified later. Why can we make such a daring assumption, right? And besides, we also assume the function is not only real, but Gaussian. Okay? The shape is fixed to Gaussian. And there are two unknown parameters to be determined. Amplitude, E0, and the pulse width, delta t. So mathematically, the steady state temporal envelope function, small f t, is written as E0, which is the unknown amplitude, times a Gaussian function, e to the minus gamma times t squared. What is gamma? So I plot the temporal intensity profile for your reference. Small a absolute square. Okay? Small a is amplitude only. Taking absolute square, what do you have? You have intensity, right? So this must be a real function. And its full width at Helm maxima is defined as the pulse width, as we introduced in lesson 1. And based on this mathematical model, you can easily calculate the pulse width parameter delta is related to the gamma parameter in this way. Square root of 2 log 2 is a constant over the pulse width parameter gamma. Okay? So simply speaking, pulse width is inversely proportional to the square root of gamma parameter in this model. Okay? And after Fourier transform, this is easy because the Fourier transform of a Gaussian function must be another Gaussian function, as you have already known. So you can carry out the calculation. This is the answer. Forgetting about the amplitude, just looking at the shape, you can see it is still a Gaussian function, right? And the width parameter is shown here. In time domain, it's proportional to the exponent. But in the frequency domain, it's inversely proportional to the exponent. Okay? So if you draw the, this is so-called power density, okay? So it's big A absolute square. Big A is the complex spectral amplitude function. Taking absolute square, you got spectral intensity or power spectrum in general, okay? And again, we define the full width at Hell maxima of your power spectrum as delta nu. Delta nu is referred to the bandwidth of this signal, okay? And you can see there is a fixed formula here, square root of 2 log 2 times gamma over constant pi. So your bandwidth is proportional to square root of gamma parameter, okay? And you have to pay attention that nu is related to omega tilde in this way. Omega tilde is angular frequency detuning from the carrier frequency omega 0. And the nu, of course, is the non-angular frequency. Okay? So these are just simple mathematical models about the Gaussian pulse in both time and the frequency domains. Any question? There's one thing interesting. If you calculate the product between the pulse width and the bandwidth, you can get a constant. Okay? Delta T and the delta nu formulas have been shown here, and you can see the gamma parameters will cancel with each other in the product, right? So the output, the product is 2 times log 2 over constant pi, which is always a constant, independent of your gamma parameter. And the number is about 0.441. This is an important parameter that you might remember, because just imagine, in the laboratory, you can easily get the red curve, right? Power spectrum can be easily measured by your spectrometer or optical spectrum analyzer, right? So this is a relatively easy information to be obtained. On the other hand, the blue curve is relatively difficult to be obtained, right? Pulse shape and the pulse duration. In the future, we will introduce how to measure them. But it's not so easy. We have no instruments directly able to measure the blue curve. So if you remember this number, you get bandwidth by your instrument. You can quickly estimate what could be the pulse duration in the time domain. Okay, just 0.441 over bandwidth, you got the pulse duration. But this is a very ideal case. It only gives you the optimal pulse duration, the shortest duration you can have. In reality, the real pulse duration, delta t, can be larger than the value you just obtained. Okay. So the product is usually referred to time bandwidth product, TBP. Okay. And another remark is this number is pulse shape dependent. 0.441 applies to Gaussian shape only. For other shapes, you got different time bandwidth products. But usually, Gaussian shape is very typical, so 0.441 is very useful. Okay, now we move on to step 2. Trace the change of the pulse due to every element. We have 3 elements. The first one is the cavity. Okay, so starting with the cavity effect. What are the effects of your laser cavity? Okay, actually you can represent the effects either in time domain or frequency domain, either way. But usually, for the cavity effect, maybe frequency domain is a better choice. We will see why a little bit later. So if we choose frequency domain, what are the two effects? The first effect is linear loss. So that means the output relative to the input, there is a ratio, e to the minus L. And the L means your loss coefficient. But this is just a constant, right? Independent of time, independent of frequency. So precisely speaking, loss effect can be represented either in time or frequency domain, doesn't matter. It's a constant only. The second effect is time delay. Okay? Say the delay is big T, the cavity gives you a delay because the pulse takes time, big T, to go through the cavity once, right? And what is the delay? It's the optical path over light speed in vacuum. And the optical path consists of LA, the path in the air. NG prime LG is the path in the gas medium. LG is the physical length of the gas medium, but you have to take into account the refractive index, right? And similarly, in the modulator, you have to take into account the corresponding refractive index. So the last two terms represent the optical passes inside the materials, including the gas medium and the modulator. Okay, so it's relatively easy. But in the frequency domain, how to represent a time domain shift? Actually, we just introduced this concept in the Fourier transform review, right? So you can represent it as a linear spectral phase modulation in the frequency domain. So this is the model. Okay. So for the purpose of illustration, let's take a look at this figure. This is your cavity. This is your input pulse in the time domain, so small l of t. After passing through the cavity, this is your output pulse. So what's the difference? Number one, you have loss, so you can see the peak is a little bit lower. Number two, you have delay, so you can see this is time zero, this is your new center, it's shifted by amount of big T. So in the time domain, this is the representation, right? But our modeling is based on frequency domain. So how to represent the effects, the two effects in the frequency domain? Maybe like this. Those are the same signal, but represented in the frequency domain, you have spectral amplitude function, big A. The solid curve means the absolute value or the magnitude. The dashed curve means the phase. So it's a real function, so the phase is constant phase. Okay? Do you know why is it a real function? Because in our previous page, we have calculated the frequency domain representation, right? This is real, okay? So what's the corresponding phase? Zero phase, right? No matter what the frequency omega tilde is, the phase is always zero. So that's why here we use a horizontal, a dashed line to represent the phase. And this is the output spectrum. Your loss will reduce the peak of your spectrum. And your delay will give you a linear shift, a linear phase modulation. So you have a tilt, a slope, right? From the horizontal line to a slope line. Okay? So this is the way we represent the cavity effect, two cavity effects in the frequency domain. Any question? if you have a positive big T, your phase function is minus t times omega. Minus t is your slope, which is a negative value. Okay. Good. Any other question? Now we can move on to the second element, the gain medium. What is the effect of gain medium? It's a little bit more complicated than the cavity, okay? So by the model of damped harmonic oscillator, the gain coefficient spectrum denoted by big G of omega tilde is actually a complex Lorentzian function, okay? The model is here, okay? This is a complex function because of the J symbol J here. And it's a Lorentzian function, also complex Lorentzian function. To represent a complex function, you need two curves. This is the choice. We have to plot the real part of the curve, which is represented by the blue one. Clearly, it's a Lorentzian function, right? The imaginary part is plotted as the red dashed curve here, which is of no specific shape that you have been familiar with, okay? So combining these two curves together, we can represent the complex Lorentzian gain spectral coefficient, okay, big G. There are two parameters in this model. Small g is here, omega g is here. What are the meanings? Small g is the peak of the real part curve. Simply speaking, it means your saturated gain, as we used in lesson 1, okay? When we talk about CW lasers, we simply model the gain is a constant gain instead of a gain spectrum. But in reality, as shown here, your gain is not a constant. It's a function of frequency. And the small g is simply the highest gain you can have, okay? The second parameter is omega g, which is shown here. And you can see it roughly estimates the width of the blue curve, okay? See the horizontal axis here. Omega tilde normalized to omega g. So when your frequency detuning equals to omega g, which is 1 here, okay? This is roughly your gain bandwidth of the blue curve, okay? Yes? Good question, okay. Let's talk about this issue a little bit later. Why is that? We have to discuss it for sure. But any question about the description of the model here? If this is true, I think the remaining things are quite easy. You can easily interpret the meanings of small g and omega g. The peak gain and the gain bandwidth, right? Just check the blue curve, okay? Blue curve. It's a Lorentzian shape. This is small g here, and the FWHM is about omega g. So peak and the gain bandwidth. Okay. But as you have noticed, we have to raise the question, right? Why is the gain modeled by a harmonic oscillator? As I indicated in the beginning, right? Damped harmonic oscillator. And based on this model, we can arrive at this formula. So do you know why? Why the gain is related to harmonic oscillator, which you might have studied in your high school years, or general physics. Okay. It's a bonus question. Let me emphasize, I prefer everyone contribute to the bonus question. So maybe I will reserve the chance for those who have never earned bonus points first. And if nobody answered, I will give the chance to the veterans. OK? 好，我鼓励大家争取这个机会，好，所以我可能会优先保留回答的机会给从来没有拿到这个 bonus points 的同学。啊，都没有人回答，我当然就让已经得过分的也回答，好吗？Simply speaking, this formula comes from the model of harmonic oscillator. Do you know what is harmonic oscillator? A spring. Hooke's law, okay? A mass attached to a spring. The spring follows the Hooke's law. So if you push the mass a little bit, then leave it alone, what will happen? It will oscillate, right? I believe you have studied harmonic oscillator before. But it looks two different, two independent things. Why are they related?
This is only my guess.
Good guess.
Okay, it is because that in the game media, the gain can come from the fall and the jumping of the electron.
Mm-hmm.
Yeah, and also you got a nucleus which is in positive, and also you got a electron negative, and it will oscillate between a certain distance. That is because of when it is emitting the light, it comes closer to the nucleus, and when it is absorbing the light, it comes farther to the nucleus. This is only my guess.
Close to. Okay. Good answer. 啊，没有错，这跟电子正电荷、负电荷互相的运动是有关的，没有错。还没有人想要试试看 ？You can speak in Mandarin if you want. I can give you a hint. Actually, in lesson 1, we model the model of plane wave, right? What does the phasor of a plane wave satisfy? E to the minus jkz, right? And if there is gain, that means when z from 0 to, for example, L, this term gives you a positive number such that you have a gain, right? So clearly, the gain comes from k times L. Okay? So can you use this hint to offer some explanation about why the gain can be modeled by harmonic oscillator? What is K? Wave number. The formula is wave number in vacuum, K0 times what? What's this? Index, good. And how do you model the refractive index? You study this in electromagnetism. Do you still remember? If not, I can show you some supplementary material. Okay. Say this is our gain medium of thickness big L. So say the distance is from z equals 0 to z equals big L. And a plane wave follows this formula, right? So the output field is equal to input field times the green part, e to the minus jkl, right? And what is k, as I shown here? N times k0. Sorry, there is no big L here. N times k0. And your refractive index n, in general, is a complex number with real part n prime and the imaginary part n double prime. If there is only real part, there is no gain. Because you can see this term will give you a phase contribution only. The absolute value is always 1. So no amplification. When do you have amplification? When the absolute value of this term is 2, you got a gain of 2. When it's 10, you got a gain of 10. But if this is only real, absolute value is always 1. There is no gain. There is no loss. Okay? But if you have imaginary part, j n double prime here, minus j times j, so what do you have? You have a real number. The absolute value is no longer equal to 1. You have gain or you can have loss. Okay? So anyway, these formulas simply tell us you need to analyze the refractive coefficient, and particularly complex coefficient. Then the imaginary part should give you the information of gain. Okay?